Okay, let me ask you a simple question. If you take a container full of gas and just lower the pressure, what happens? Your first thought, your intuition, probably tells you it expands, right? It becomes even more of a gas. But what if I told you that under just the right conditions, dropping the pressure can actually cause that gas to start turning into a liquid? Yeah, I know, it sounds completely backwards. So let's explore this wonderfully strange behavior.
So, here's how we're going to break this down. First, we'll start with the simple rules, the stuff we all think we know. Then we'll see how a mixture, like natural gas, just throws that rulebook out the window. We'll learn how to read its unique map, this phase envelope, and then we'll see some truly weird physics in action, before finally talking about why any of this really matters in the real world.
All right, before we can get to the weird stuff, we've got to build a foundation. Let's start in the world where the rules are simple, predictable, and make a whole lot of sense.
Okay, so think about that question again. Your intuition is probably based on your experience with simple, pure substances. And you know what? For those, you would be absolutely 100% correct.
For something pure, like water, this right here is the rule book. It's a phase diagram. It maps out its state, solid, liquid, or gas, based on temperature, that's the bottom axis, and pressure on the side. The lines are nice, clear boundaries. If you keep the temperature steady and drop the pressure, a liquid boils and turns into a gas. It's simple. It's predictable.
Now, check this out. This one spot on the diagram is really interesting, the critical point. If you go past this point with enough temperature and pressure, the whole distinction between liquid and gas just dissolves. The substance becomes this weird, high-energy state called a supercritical fluid. It flows like a gas, but can dissolve things like a liquid. This is basically the absolute upper limit where the simple rules apply.
Okay, so we've got the basics down. But what happens when we're not dealing with just one pure substance, but a whole cocktail of them? Well, this is where things get complicated. And this is the whole key. Natural gas isn't just one thing. Yeah, it's mostly the lightweight stuff, methane, but it's also mixed with heavier molecules, things like ethane, propane, butane, even pentanes. And that complex recipe completely rewrites the rulebook we were just looking at.
So forget those simple lines. This is our new map. It's called a phase envelope. It still plots pressure versus temperature, but its shape, this kind of tilted, dome-like thing, that immediately tells you we're in a whole new territory. Outside this dome, it's simple. You've got a single phase, either all liquid or all gas. But inside the envelope, that's where liquid and gas exist together in a really complex balance.
So we have our map. Now we just need to learn how to read it. Let's go ahead and identify the key landmarks that define this new terrain.
Okay, think of this envelope as having two different coastlines. The one on the left, that's the bubble point line. If you start with a liquid and you drop the pressure, this is the exact line where that very first bubble of gas will appear. Now the right-hand shore, that's the dew point line. If you start with a gas and cool it down, this is where the very first drop of liquid, like dew on the grass, will start to form.
Now let's look at the absolute limits. The farthest point to the right on this whole envelope is called the cricondentherm. The name itself gives you a clue. Cricondentherm. Think therm for temperature. This is the absolute maximum temperature where you can possibly find liquid and gas together at the same time. You get any hotter than this, and it doesn't matter what the pressure is, it's going to be pure gas.
And then, the highest pressure point on the envelope is the cricondenbar. Again, just think bar, a unit of pressure. This is the maximum pressure where liquid and gas can coexist. But notice something a little weird. It's often at a much higher pressure than the mixture's critical point. It's just another way mixtures defy our simple expectations.
Okay, we know how to read the map now. We've identified the borders, so let's take a journey right through the heart of this envelope to see something that seems to completely break our intuition.
This is our travel itinerary. We're going on what's called an isothermal journey. It's just a fancy way of saying we're going to follow this straight vertical line, keeping the temperature perfectly constant. The only thing we're going to change is the pressure. We'll start way up high at point A and just move straight down.
So here are the steps of our journey. We start at point A, clearly in the single-phase gas region. Now, as we drop the pressure, we cross the dew point line at point D2. We keep dropping the pressure, traveling right through this two-phase region, and eventually we cross the bubble point line and pop out the other side, back into a single-phase gas down at the bottom.
But let's pause. Let's pause right in the middle of that trip. We are dropping the pressure. Everything we thought we knew says this should keep something a gas, or maybe turn a liquid into a gas.
But inside this envelope, the complete opposite is happening. Liquid is actually forming. How? Why?
Well, this crazy phenomenon has a name. It's called retrograde condensation. Retrograde literally means backwards, and that's exactly what's happening. Think of it this way. That really high pressure is like a physical cage, just forcibly cramming all these different molecules together into a gas. The heavy ones, like propane and butane, they'd much rather be liquids, but the pressure is so intense it gives them no choice. Now, as you lower that pressure, the bars of the cage start to spread apart. The lightweight methane molecules, they're happy. They expand and fly free. But the heavier molecules, with less force holding them in the gas phase, they can finally link up with each other and drop out as a liquid.
So this isn't just some cool, abstract science fair project. Understanding this backwards-seeming behavior is absolutely mission-critical for the entire natural gas industry.
I mean, just imagine you're an engineer. If you don't account for this, unexpected liquid can form in your pipelines, choking the flow like cholesterol in an artery. Even worse, these slugs of liquid can slam into a compressor turbine spinning at thousands of RPM with the force of a sledgehammer. That's a catastrophic failure. But on the flip side, these natural gas liquids are super valuable. So by controlling this process, you can efficiently pull them out. It's all about managing that dew point to deliver gas that's clean, safe, and on spec.
And this quote really gets to the heart of it. Controlling these phase changes isn't an accident. It is a deliberate, essential part of processing natural gas. Engineers will actively cool the gas to force it across that dew point line, which lets them remove those valuable and potentially damaging liquids in a totally controlled environment.
So what we've seen is that simply mixing a few things together can turn our basic understanding of physics completely on its head. It really makes you wonder, doesn't it? If something as fundamental as pressure can behave this unexpectedly in a mixture, what other so-called simple rules are just waiting for the right conditions to show us a much deeper, more complex reality?